module at the Goddard Space Flight Center. And of course, everyone has had to contend with the global pandemic, Snowmageddon, while testing the Integrated Science Instrument Module at the Goddard Space Flight Center. And of course, everyone has had to contend with the global pandemic. One particularly memorable challenge was working through Hurricane Harvey in 2017. This massive cyclone dumped 60 inches of cryogenic testing at NASA's Johnson Space Center. Though the telescope remained safe inside the test chamber, water leaked through the ceilings, people had to cover workstations in plastic tarps in short supply, and a few team members trapped by floodwaters had to be rescued by boat. It was rough, to say the least, but the team and the telescope survived the storm. Despite winds and snow and endless rain, the team got it done, and Webb is now ready for its final journey atop a rocket into space. While the Webb telescope is a technological marvel, everything here began with questions. Questions about how the first stars and galaxies came to be. Questions about whether planets like other stars might have environments that can sustain life. And of course, the promise of discoveries we can't even predict yet. A few days ago, I had a chance to speak with someone who's probably the best person on Earth to help us understand what we know, what we don't know, and how Webb will help fill those gaps. Dr. John Mather is a Nobel Prize holder who measured the Big Bang with an observatory built here at NASA. John is led senior project scientist. We're so pleased to have you here today, John. So, to start this incredible story, Webb, let's start with something that's deceptively simple: gravity. Something special.
Gravity is special. Gravity always pulls. It's the only force of nature that always pulls. So that's special. Yeah, what makes that special is that gravity, although it's very weak, is very long range. It sweeps across the universe. Yes, because it's always pulled, it's possible for gravity energy. Energy to be converted into kinetic energy, just heat, and the universe becomes self-heating, which is not something other forces could do all by themselves. Clouds of gas can be compressed by the gravity until they get big enough and hot enough to light up and have the nuclear reactions inside that turn hydrogen and helium into the chemical elements you see around you, here in the house, here on the set. So carbon, oxygen, nitrogen, everything we have that we think of as ordinary came from inside stars. So we are stardust, as Carl Sagan told us, but there wasn't any stardust in the Big Bang. So we need this part of the story to be figured out. How did we come to be able to live here on our little planet when the universe started out without all of these goody things?
So you mentioned these planets around other stars. So we're almost sort of going through all these amazing science schools of the Webb. What can Webb tell us about planets around other stars?
Well, once in a while, a planet goes in front of the star, and some of the starlight goes through the atmosphere of the planet. If it has an atmosphere, on its way to the telescope, we will spread out that light into a spectrum, or
Webb launches, one of my dreams is I'm going to be standing outside of my backyard and say there's a planet around that star that we know has water vapor, oxygen, carbon dioxide. So what is Webb going to also do in the search for life closer to home, our own backyard?
Well, here in our own solar system, we will be looking at everything from Mars on outwards to the farthest we can see. Satellites, That's a good clue. So the satellite Europa, which orbits around Jupiter, was discovered by Galileo himself. And we know now that it has an ocean that's covered with ice. There are cracks in the ice where water comes spitting out. NASA are going to send a probe over there to fly through those plumes. We're also going to point over there with the Webb telescope to see what can see about that atmosphere and those plumes of water. We'll be looking at Titan, which is a satellite of Saturn, which is so big that it has an atmosphere enough to fly a helicopter. And it is cold out there, so that what they have, what is on the surface, is solid ice. And over that are liquid hydrocarbons, which you use for fuel here in your home. But over there, it's liquid rain, lakes and rivers, and we'll be looking at the geology of that before we send the helicopter out there.
So you're on this amazing journey from the very distant early universe all the way to our own solar system. But this has also been a personal journey for you. You've been working on Webb since the very beginning of the mission. Is that correct?
I have since '95. We had our first conversation, but people were even dreaming and imagining way before that what we needed. And you could tell even before we launched the Hubble what were the possibilities. And we learned that we would need an infrared telescope that could do things that Hubble could not do.
Well, John, I've been an admirer of yours for many decades now, and it's an honor to be with you on this part of the mission. So thank you so much for joining us. Best of luck on the launch and the mission ahead.
Thank you for asking all these great questions.
The Hubble Space Telescope delivered profound insights about our place in the cosmos. But perhaps the biggest takeaway from Hubble is that we've only just scratched the surface. Hubble gave us the best ever views of stars and planets forming inside vast, dark clouds of dust. But as soon as we had that data, we were asking new questions that needed better measurements, clearer images. Hubble was also able to capture images from galaxies so far away. Their light took 13 billion years to travel to us. These distant galaxies are just tiny dots in Hubble's images, tantalizing scientists with clues about how the first galaxies formed. In order to pursue a better understanding about the earliest days of the universe, we needed to build a better time machine, and that's Webb. So I'm going to be rejoined here by Nicole and Macarena, and this is our chance to talk a bit about building that better time machine. What about the technology of Webb? So there's so many aspects of Webb to start off with, but maybe again, going back to the theme of infrared. The design of this telescope is so different because we had to use infrared light, heat light. So tell us about some of the challenges of, for example, why does it have to be so cool? Tell us about infrared light and the design.
Right. Well, I think we've heard already just how cool it has to be. It's around or below 50 Kelvin, and that's minus 370 degrees Fahrenheit. Actually, below that is what it operates at. And that's very cold. And the reason we need it so cool is because we don't want the telescope itself to detect itself. Because there's several instruments on board. There's 4 different instruments, and there's some moving parts. And so you need things to be cool because you want to detect these faint signatures from either an exoplanet atmosphere or faint light from the earliest stars and galaxies. So you just don't want to detect your own telescope.
And Macarena, you are the instrument calibration scientist for the coolest instrument.
It is the coolest
on Webb.
instrument.
Miri. So tell us a bit about Miri and why it needs to be so cold.
So Miri, it's a really unique instrument, and it's a great example of this collaboration we have in this mission because it's half European, half US. So Miri is the only instrument on board that uses the mid-infrared light. And the mid-infrared light is a bit cooler than the near-infrared light. And so because of that, Miri needs to be colder in order to detect that very faint signal from high-received galaxies or protoplanetary disks, etc. So because of that, it's the only instrument on board that has a cryocooler. So it is not only the passive cooling from the sun shield, it is active cooling. And it brings it down to about minus 450 Fahrenheit. So it's degrees above the absolute zero.
And we were talking about you don't want the telescope to be so hot that it's basically giving off its own signal, its own radiation, and that leads us to why it needs to be in space, right? So tell us a bit about why do we need to launch this thing into space to see these wavelengths?
Well, again, it kind of goes back to atmospheres because Earth has an atmosphere and there's water in Earth's atmosphere as one example. I mean, there's a lot of other molecules, but wavelengths that we want to observe in planets and galaxies, those wavelengths are actually where Earth's atmosphere is opaque. So with telescopes located on Earth, even
at higher mountains where they try to get above the clouds or atmosphere sometimes, there's still residual atmosphere that we're trying to look through and peer through. So in order to see the full infrared wavelength range at a very high sensitivity as well, we need to go to space. Absolutely. So we talked about spectroscopy.
It's a small wire inside, and then we have a spring that unwinds and allows two halves of a split nut to separate, and then our pin can get extracted. And so in the case of the MRDs, it's a spring-loaded pin that pulls to release the folded membranes. In other places, we would be bolting two pieces of structure together and then releasing them so we can deploy them.
And the sun shield itself has 107 of these?
107 MRDs that all have to work.
Every single one has to work.
Every single one has to work. And 178 of this type of device in various configurations around the entire observatory.
Right. Well, if we go over here, we've got something sort of lovely waiting for us, a big gold hexagon. So to tell us what we're looking at, a sort of a model here of the mirror segment.
Right. Full 18 mirror segments on James Webb. The real ones would be machined out of a single piece of beryllium to the exact curvature we need. And then once we're deployed on orbit, each segment can be individually focused to make it act as a single perfect mirror.
Now that coating, tell us about this gold coating here.
Yeah, so this is shielding.
NASA and the James Webb Space Telescope. NASA is hosting an Unfolds the Universe Art Challenge. Use your imagination to share what you believe the Webb Telescope will find.
Believe that the Webb's telescope will see galaxies, stars, planets, the moon, and don't forget our star, the sun. Up in the sky, really high, it's space.
Ooh, space. Thanks, Greta. Good job.
This is my picture of space. Hello, my name is Gabriel. I am from Romania. This is how I imagine space. Hello everyone, good morning. This is a drawing of distant galaxy that can be seen by James Webb Space Telescope. Hi, my name is Anastasia, and this is what I think the telescope will look like. What the telescope will see. I do the Earth, the Sun, a new planet, black hole, and stars.
So we've been fielding social media questions from viewers all over the world this morning, and let's take a couple of minutes to share some responses. There's been a couple questions about how long will it take for images to come out, and there's a lot of things that need to happen before the images are coming. So Macarena, why don't you take us through some of that?
Yes, so for the first scientific, beautiful images to share with the public, that'll take 6 months. The reason is because it is, so we launched today, it takes a month to take to the orbit place, to the Lagrange 2 point, and then we have a whole period of cooling down the instruments, aligning the mirrors, and making sure that all the instruments are ready to do science. So the whole process takes 6 months, half a year.
And also,
जो भी कर देना सब दिखाई दे रहा है